Okay, let's look at a modulus of elasticity example. So let's look at a modulus of elasticity example. If we have our same cube of steel, that is 25 millimeters by 25 millimeters by 25 millimeters, and it has deformed 1 millimeter, what is the force on the cube? We want to know what force caused that deformation. Well, lucky for us, we know the area is 25 millimeters by 25 millimeters, which is 625 millimeters squared. We know the original length is 25 millimeters. We know the change in length is 1 millimeter. And we know the modulus of elasticity of steel. It's one of the few things I'm making you guys memorize. And it is 200,000 MPa. Well, we know that E equals PL over delta L A. I just found a typo in the slide that I just want to remind myself to fix. So E equals PL divided by delta L A. And we want to know what P is. We know E, we know L, we know delta L, we know A. We can rearrange this if we want. We can say that P equals E delta L A divided by L. So we can plug all of this in. We have E is 200,000 MPa times our delta L, which is only 1 millimeter, times our area, which is 625 millimeters squared, divided by our original length, which is 25 millimeters. We can plug this into our calculator. 200,000 times 1 times 625 divided by 25. We get 5 million newtons. Well, that seems like kind of a crazy number. It's a bit of a pain to talk about this in newtons. Let's talk about our force in kilonewtons, just because now that we're talking about a force, we like to switch back to kilonewtons. So there are 1,000 newtons in a kilonewton. We've got 5,000 kilonewtons. So for that cube to deform 1 millimeter, we needed 5,000 kilonewtons of load. One of the other examples we did shows us that the maximum load that our cube could take was 218 kilonewtons. Well, this seems to be greater than the P max of, I think it was 200 and, what did we calculate? Where is that example? Where did that go? Here it is. 218.8 kilonewtons. So we would fail our cube. Interesting. We haven't talked about what that means, but basically we'd squash that cube past any sort of linear deformation. We'd cause some permanent deformation in that cube. When that load got removed from it, or those 114 elephants got off of that cube, all of a sudden this wouldn't spring back to its original shape. It would experience permanent deformation. So let's do another modulus of elasticity example. Let's do E for rubber. Let's do the modulus of elasticity of rubber. Somebody's telling us that the E for rubber is 55 MPa versus our steel, which had 200,000 MPa. They're telling us that delta L equals 1 millimeter. It's the same 25 millimeter cube. I mean, it's a different material now, but it's 25 by 25 by 25, which means we know the original length was 25 millimeters, and we know the area is 25 by 25, or 625 millimeters squared. So we know original length, change in length, E and A. We know that the equation is E delta L A divided by L if we want to determine P, or 55 MPa times our 1 millimeter times our 625 millimeters squared divided by 25 millimeters. Our force is going to equal 1,375 newtons, but we like to talk about these things in kilonewtons, or 1.38 kilonewtons. So for this particular rubber cube that's 25 by 25 by 25, it's going to take 1.38 kilonewtons to squash it. That's still more than Arnold would weigh. That's about 309 pounds. So this seems like a really stiff rubber. We could probably find different rubbers that have a much smaller E or a much smaller modulus of elasticity. So you can see that the relationship between E really has an impact, that the E of a material really has an impact on how much load it can take to deform the same amount, or the deformation can change depending on how much we load it. So this relationship between force and modulus of elasticity, change in length, and area is very important from allowing us to take a very small object and extrapolate into a big object.